So today we're also finishing up the, this is called the Planck distribution. I realize I haven't told you that. The energy output of a light bulb, it follows what's called a Planck distribution. A Planck distribution is the spectrum of a light bulb, spectrum of the sun as well, because a light bulb is a miniature sun. It's just a hot ball. The sun is a hot ball, it's just way bigger. They both produce light via the Planck distribution. And that's actually what we're solving. I never named it. It didn't. Just a factoid. So we're going to finish that today. And then we're going to go into some other little details, things that kind of got people thinking around 1930. I think it's 1932. Science moves slowly, so early 30s. That made people start to think of what quantum mechanics was, the things that kind of pushed them in that direction. So we're going to cover that as well. Any questions before we... no questions, so it's kind of good. Look, heads up, this is kind of painful, all right? We are now finishing up this derivation that will have taken 3 lectures, right? And today is the worst part. I've done nothing. I spent all morning actually rewriting my notes. I actually rewrote my notes twice, trying to make it as clear as possible, mostly to myself, because some of the things we're going to do are just going to be kind of funky, and there's going to be equations, a couple of them that go across the board. Anyway, so before I scare you, before you actually see anything, remind you, okay, we want to get the energy out of a light bulb. Big goal here. Now we're going to do this by we got some energy of light, but we're going to have a Boltzmann factor that tells us how much light is present. Now you may notice I've set up an average value, right? If I had velocity times the Maxwell-Boltzmann distribution of velocity, that would integrate to average velocity. So what this guy is going to end up doing is it's going to give us average energy. Now that's going to be for a wavelength, but the summation is going to be over all wavelengths. A light bulb could produce basically any wavelength. Actually, they can't be too long. They can't be longer. The wave can't be arbitrarily long. They have to be about the same size as the light bulb, and then they can be shorter. Okay, so wavelengths, average energy of the wavelengths, degeneracy factor. So that's what I spent really all last lecture on. I hope it wasn't terribly confusing. But recall that we started all of this on Monday looking at these sets of X, Y, and Z numbers that tell us how many nodes the wave has inside the light bulb. So 111 is no nodes. The wavelength was twice the length of the light bulb. And again, I'm just reviewing what we covered last time. Okay, now from that, I'm able to describe 111 by nx. Remember that we call these mode numbers. Nx squared plus ny squared, ny squared plus nz squared gives me n squared, which would be 3. And recall that I'm able to relate this to the wavelength of light. Now, the wavelength of light will give me energy, which is going to appear here. So that's why I'm doing this. Okay, big picture. We were able to describe n squared, which is basically the number of nodes, which then tells me the wavelength of light, which tells me the energy. So n squared is incredibly useful. It's the thing that makes sense. This is basically the energy. It's just that I've got to convert this to wavelength, and then I've got to convert it to energy. Whatever. This is basically related to the energy. That's awesome. But just like when I was trying to convert partial Vx, partial Vy, partial Vz, I was trying to convert those to partial net velocity, because net velocity is the thing that's sensible. Net velocity is related to the energy, 1/2 mv squared, net velocity squared. The problem is you can't just change partial x, partial y, partial z into partial net, because there's a scaling factor, right? 4 pi v squared. That's why when we went from partial Vx, partial Vy, partial Vz, it actually was equal to 4 pi v squared partial v. Anyway, just reviewing. We have the same problem here. This is useful, but we have a degeneracy problem, and that's this part here. Okay, and the way that works is for the longest wavelength, which would be the 111 set, no nodes in X, Y, and Z, there's one way to write 111, right? Because they all look the same. Okay, for a wave in X that's actually, has a node and the others don't, we actually have 3 of those, because I can write 211, 121, 112. So there's 3 of those, and I have this running total. And yada, 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 yada.
60, 60, 60, square, the sum of the squares is 10,800. There's 91 of these. Now, one of you was asking me after class, they're like, no, wait, no, there's only one 60, 60, 60. There's other 3 sets of numbers that total to 10,800. There's 91 of them. I can't write them all down. I actually used a computer. I had to use a computer to search for a couple hours to figure out that. So again, there's other 3 combinations of 3 numbers, square them and add them that equal 10,800. There's 91 of them. 60, 60, 60 is just a nice one. And on and on and on. And so you can see how the running total increases. And the point of last lecture was that that's basically 1/8 the volume of a sphere, which is pi over 6 m cubed. Okay, so still just reviewing. Now what we did with this thing, now again, also recall energy, energy, but we need to take this into account, and we take that into account, just like the 4 pi v squared is basically this pi over 6 m cubed. Then what? Okay, what do I want to do with that? I want to then plug in, when I'm going to solve this thing, if you see what I'm trying to solve the energy, I'm going to do this as a function of wavelength. So I need to turn this degeneracy factor, I need to express it in wavelength, or I've got a bit of a, I don't know that I'll be able to solve that final energy thing that well. Now from the Maxwell equation, the E&M equation, remember that we figured out that n squared was actually 4L squared over lambda squared. Okay, 1/6, the degeneracy factor, 1/6 n to the 3 is 1/6 pi n squared to the 3 halves, and this ends up being 4 pi over 3 L cubed over lambda cubed. But then we've got to times 2 polarizations. Okay, it's like a degree of freedom. We have left and right circularly polarized light. That's also on your homework. I have a nice drawing of what left and right circularly polarized light. And therefore the degeneration factor is actually 8 pi. Again, a little factoid, but we do need to keep that into account, or the sun is only half as bright. Now, another thing to note, that this is also the running total, just like I've done in here. So, you know, there's 1 in the set of 1, 1, 1, 3 in the set of 2, 1, 1, and so I have the running total of 3 plus 1 is 4. Anyways, that's obvious. That's what this is. That's actually going to be a little bit of a problem. Remember how, when we were doing Maxwell-Boltzmann, dvx, dvy, dvz was the surface area of the sphere times the change in radius, 4 pi v squared dv. This is not the surface area, so that's a bit of a problem. I can't quite use that as is. It's not a degeneracy, it's the total. So I'll show you how that gets taken into account later. Again, I mentioned to you that unfortunately today's lecture is a little bit complicated. And that's one of the things that kind of monkeyed this up. So another thing I want to point out, let's go back to our big goal. We actually don't want to do this either. We want to not solve for energy, we want energy density. And this is pretty obvious because back in the day, remember, a lot of things got moving in the scientific world. You know, 1900 was a huge, 1880 to 1930 we were almost living in the Stone Age to nuclear weapon land, all within that span of 50 years. And electricity has almost everything to do with it. So when we had electricity, we built light bulbs, but no one's light bulbs were the same. And so to normalize this, everyone just divided, to make sure that all this made sense, they built light bulbs, but they had to divide out all their numbers by the size of the light bulb so that everyone could compare their results, right? Because a bigger light bulb produces more energy. So that's just another little extra bit I have to throw at you that I don't think I mentioned that before. Maybe I did, but anyway. All right, so, and I'm still reviewing. I was just like, I'm already kind of confused and I'm just reviewing this as a lecture. Okay, next bit. Now we're going to actually get into the material at this point. All right, now look at this guy. This is obvious to me that when I've got energy times a Boltzmann deal, what this is going to actually be is average energy. And I need this as a function of wavelength because I need to sum up the energy of all the waves that are in the light bulb. And remember that goes back to this part right here, right? So there's a limit. So a 1 centimeter light bulb has a 1 centimeter wavelength photon, but it can have infinitely smaller number of shorter wavelengths. So that's another complication again. But okay, so now let's work on this part here. Energy times a Boltzmann factor. It looks to me like I'm going to end up calculating the average energy. It looks like another Maxwell-Boltzmann equation. It is. It's just for energy of a photon as opposed to average velocity. And this is it's a reason I do Maxwell-Boltzmann first. So this is like Maxwell-Boltzmann velocity. Actually, it's energy. You even did energy on your homework. But we've got, the reason I do this after Maxwell-Boltzmann velocity of a gas is because we have this extra complication. It's like there's more than one type of gas. That's kind of like how you might want to think about it. Okay, so now how do I deal with this thing? Now, another interesting thing about this equation is it shows you a little bit more about what Maxwell-Boltzmann distribution does. When I introduced Maxwell-Boltzmann distribution, I just said, this is how nature partitions energy. And here's the equation for it. Okay, what do you do with probability distributions? You multiply it by the thing you want the energy of, then you integrate it, and you get the average. And I bet maybe it got a little bit lost, but what really is a Maxwell-Boltzmann distribution? Let me show you what it does. This is kind of neat. Okay, so let's look at the energy of light is hc over lambda. We know that. Actually, I'm going to explain a little bit where people figured that out. Let's divide that by kBt. Now you know that the Maxwell-Boltzmann distribution has e to the minus energy over kBt. Energy over kBt. Okay, so what? Okay, if I plug in a light bulb, it's about 1 centimeter. So let's plug in a 1 centimeter wavelength, and let's be at 298 degrees K. Okay, so that gives me the energy. kBt is done by temperature, and this would be about 1 over 200. That's what that does. That's what this is. Okay, Maxwell-Boltzmann is not okay with this. This, if I allow this to do what I just wrote, for the photon to have 1/200th of a kBt of energy, Maxwell-Boltzmann, I can tell you, will not be satisfied. Maxwell-Boltzmann says, no, energy is not being partitioned the way I dictate it is to be partitioned. When Maxwell-Boltzmann is happy, I can tell you in all honesty, this will be about 1. It'll be about 1. Now, it kind of makes sense, right? E to the minus 1, right? That's, you know exponentials. When you get to e to the minus 1, it's when that factor kind of starts to go away, right? So that's why you find that this tends to happen. Okay, now I think I talked about this a little bit last time, so maybe you already know the answer. How do I make this happen? Do you recall? I think I said last time, didn't I? Now, the energy of one photon, for a light bulb's about a centimeter. That light bulbs are about a centimeter big. Room temperature is room temperature. I know they're hotter. Let's just do this. And yet this is 1 over 200. So how do I get that energy back up? How do I jack that up? Because I can't change the wavelength. I can't change what it is. But how could I boost that up? How can I get more energy in the 1 centimeter, for the 1 centimeter wavelength?
Multiple photons?
Yeah, multiple, right. Remember I mentioned this last time. Who says that, remember I just drew a wave? Here's the light bulb, here's the wave. And I said, who said there's just one wave in there? right? Oh, is it because only one way fits? Well, I'll build a bigger light bulb. Right, that actually just doesn't even make any sense. Remember I was asking you, how big is a photon? The photon is about as big as its wavelength, by the way. All right, so the answer is, and unfortunately, I am sorry about this. Okay, we're going to have n photons. Unfortunately, that happens to coincide with the mode number. Sorry, it's a different n. I've run out of letters. That sucks. But this is how we tend to do it. So. Oh God, please don't let that get confusing. This is number of photons. Nothing to do with this, nothing to do with that. Sorry, just this is out of letters. This does happen, right? Remember, E was electric field. That's why I've been writing energy. We started on Monday. E was electric field. That's why I'm always writing energy, because I don't want to get that confused. This, I was staring at this for like an hour trying to think of big N or something like that. I just couldn't think of anything, so I'm just going to this is how you see it online anyway. Okay, so Maxwell-Boltzmann solves this dilemma by having more photons present. So now hopefully you can see something. When I have low energy photons, like 1 centimeter, right, that's like cell phone range, by the way. I'll get a lot of those. But when it comes to X-rays, and that's a short wavelength, that means it has high energy, nature will not allow any of them to exist, right? Because then this ratio would be very large without... So if I'm talking about X-rays, an N of 1 has this ratio like way too big. And so what nature does is it doesn't allow a light bulb to produce X-rays. So that's, anyway, just a little bit more. So I'll show. All right, everyone. So I have made a break in the video because I made a slight mistake when I was calculating the average energy for photons of wavelength lambda. The derivation I was kind of breezing through is a little complicated. So what I was trying to do was take a multi-step derivation and just say, here's the setup, here's the hat, here's part of it, and then here's the end. And I made a slight mistake in the middle part, and it just bothered me. So I thought I would just do it for real. Work through the whole thing. And there's a handout on the web as well. So now again, and this is a little bit of a pain, but I don't like the thought of not having it done correctly. So I went ahead and thought I'd just come to the classroom and show you how it works and just insert this, which is what I'm doing right now. So what we were trying to do is calculate the average energy of a photon by the energy times the Boltzmann factor, and looking over all possible energies. And of course, as usual, the Boltzmann factor is e to the minus energy over kT over all possible energies. Again, kT is our weighing factor. And here's where this gets kind of funny for photons. Nature will change the energy of whatever you're talking about to conform to the Boltzmann distribution. Now, that's a little funky for a photon because its energy is only determined by the wavelength. So what does nature do? Nature changes the number of photons. Okay, the way that looks is, again, the energy, if you add or take away photons, you're adding or taking away energy. So that's how nature does it. So we're going to call n the number of photons, and of course the photon energy is hc over lambda. Let's not forget our kT, so that's on the bottom. And then we sum over all possible energies, but the way that works is nature could have no photons, which is no energy, or an infinite number of photons, which is infinite energy. So the sum over all possible energies is a sum over photons, right? Because that covers everything, no energy or infinite energy. I don't know that we could span further than that. All right, so there you go. Now, here's where I actually flubbed it, by the way, which is the normalizer. How do you do the normalizer? Now, when we were doing Maxwell-Boltzmann velocity, that turned into an integral, and so one of the reasons I wanted to not do this is because you don't have to do this with an integral. And I didn't want to have you like, wait a minute, when is it an integral, when is it not? It is an integral when it needs to be, and it's not when it doesn't need to be. In this case, I have a formula to solve this without an integral. I just look it up on the web. I find This little formula, a to the n, the summation of a to the n when n goes from 0 to infinity is 1 over 1 minus a. And so I can apply that here, and I don't need an integral. Again, I don't use an integral because I don't need one. All you have to do, as usual, when you have a problem and the cheat sheet gives you the answer, you just got to figure out how to use the answer. And in this case, you just recognize that n here is the same as the n here, oddly. And that means that a is actually e to the minus. Minus is still there. See, there's no minus. Minus is still there. hc over lambda kt. Okay. Now that we have that worked out, I'm going to go ahead and calculate the average energy of a photon. And let me just show that we're doing a break. So the average energy for a mode, remember we're talking about a light bulb. A mode has an associated nx, ny, nz, a net n squared, which is what gives me a wave loop here. Okay, and so as usual, this will be the energy, and we still see n show up, n number of photons, hc over lambda, which is the energy of a single photon. Oh yeah, that's it, there's no kt. So that's the energy of the photon, n photons of that wavelength. We've got the business n, now we've got the maximum Boltzmann factor, minus nhc over lambda kt, and then we've got the normalizer. 1 minus e to the minus hc over lambda kt. Okay. But now, like in Maxwell-Boltzmann with velocities, you're used to there being an integral. In this case, there isn't one. Now let me explain why. I told you in class that the correct definition of an average of a property, and I call the property y, y can be velocity here, is energy. The average value of a property y is the integral over all values of the probability of that property times that property, and of course there's a partial, the spread. Okay, the reason we did that was because we were doing velocity, and velocity is continuous. When you're doing something that's discrete, when you're calculating the average value of something that's discrete, so this is for continuous, if you're discrete, the way that works is it's just a sum over all values, probability times the value. And this again is for discrete. And if this was an exam, I would now ask you, what does discrete mean? Discrete means that unlike continuous velocity, which can have any value, discrete means 0, 1, 2, 3, 4, 5. It means it's an integer. So in the case of photons, it's discrete. There's either 0 photons or 1 photon or 2 photons. So we're actually going to use this formula here. This is actually easier to understand than this. I started out with this because that's what we were doing with velocity. But now here's an example in finance that we often use. If a manager is trying to value a project and they don't know what's going to happen, let's say that either the project will generate $1 million and there's a 50% chance of that, or it could generate $2 million and there's a 50% chance of that. What they expect is that the average value will be 150 million, right? So there's 50% chance of $1 million and 50% chance of 2 million, so that's 0.5 times $1 million plus 0.5 times 2 million, that's 1.5 million, right? That's sensible. So this is actually easier, it's just that we don't always have discrete things, but we do here in the case of photons. So that means that the average value is the sum of there being maybe no photons or infinite number of photons, and there you go. All right, now to solve this guy, like last time, because we have a discrete thing, I can just Google an identity, and here's the identity, n a to the n, and this is equal to a over 1 minus a. It looks similar to what we had last time. And like last time, we just have to recognize okay, there's a bunch of constants that have to come out. We have to recognize what A is, and A is actually the same thing as last time. It's e to the minus hc over lambda kt. Despite the fact I'm in here by myself, I'm using the board just as well as before. Okay, so regardless, let's take out all the constants. So that's hc over lambda. Now, you may be saying, hey, wait a minute, where's the n? Where's the n? The n is right here, right? N, a to the n. N, a to the n. So the answer doesn't have an n in it, right? So that's why that just plops out as it is. Here's the normalizer from the Boltzmann distribution calculation. Okay. Then we've got A, which is this thing here, the business end of the the Boltzmann distribution. Sorry, there's no A, has no n in it. You see, I just almost messed up. It's just hc over lambda kt. And now you see why this is going to work out real nice, is because 1 minus a squared is actually this thing. See, it's almost the exact same thing as what we were doing when we were normalizing Maxwell-Boltzmann. So, and we're done now, by the way, but let's simplify it a little bit just because we can. This obviously cancels, so it ends up being not too hard. Hc over lambda times e to the minus hc over lambda kt, and 1 minus e to the same thing. Okay, but now you know what? There's this well-known trick to simplifying this further. Let me show you that, and then this gives you the answer I gave in class. It turns out that you make this way easier by multiplying top and bottom by e to the hc over lambda kt to the positive. Notice that these get canceled out, that's the number 1. Now again, we're multiplying by 1, so e to the hc over lambda kt on top and bottom. Okay, so you see what happens. You end up with the formula I gave in class, so there's an hc that survives on top, and the bottom is lambda. This is e to the hc over lambda kt minus 1. There you go. Okay, and that is the average energy for a photon mode of wavelength lambda. Then we insert this into the remainder of the Planck distribution, and now I'm cutting back to the class. Any other questions? Okay, back to the above. Energy density, sum of wavelength degeneracy times average energy. I've got that part done. Now let's finish it. And now we run into another hideous integral. All right. Oh God, and we run into a new concept that you haven't seen before. And in fact, also, when I was talking about how I had a hard time with this doesn't really bother me. This next part does, which is how we count for the degeneracy. So, sorry, I should have left. Oh, damn it! Sorry, I shouldn't have deleted all that. I can just work downward from this because we're still just we've been trying to solve this the whole time. Okay, so now remember that so I'm gonna do this guy now. Let me just break that back up. Okay, 1 over L to the 3, and this is the energy density. Okay. The thing that kind of slays me here, as much as we've got a real simple formula for this now, but remember that degeneracy factor, that 8 pi L3 over 3 lambda cubed that we spent the first part of this week on? That is the running total of the number of modes as a function of wavelength. That's not really a degeneracy. So you have to do something kind of funky with that. Here, let me, what am I? I'm just writing this again for the zillionth time. H HC over lambda BHC over lambda AB. So we just did a lot of work to solve this, and it bothers me that I don't have the top centered. It must be perfect or the world explodes. There we go. Okay, so I've got that part. Okay, now what do I do with this degeneracy thing? Okay, now remember, it's a running total, but that's, but I need to know the number of 211, 121, 112. I need to know what that number is, that degeneracy, not the total, but the per wavelength. Not 4, but 3, if you recall that I had just raised the GoB. Okay, now the way you do that is, now the degeneracy factor, you might, if you're following along here, you might want to leave a lot of room. Remember that this is 8 pi L cubed over 3 lambda cubed. Okay. Here's how you deal with this. Running total doesn't help. What you're going to do is you're going to take the change with respect to wavelength. You actually need to take an absolute value, and I'll explain that in a minute. But you need to fix the fact that you divided by a partial, by multiplying by a partial. Okay, let's not forget this one over L to the 3. And now I got a partial. As much as I was yapping and yapping about not needing to do integrals, here's an integral. Right? Bang your head against the wall. This just goes on and on and on. It's like never ends. That's why, the big reason I film this stuff is because, holy crap, we're doing a 3-day derivation. And we're done now. Almost. We have to just do some details. Notice that. Okay, here's where it gets a little funkier too. The lower will be 0, but notice that 0 wavelength. That actually corresponds to 0 wavelength photon. Is that high or low energy?
No, it's
No, I got you. What
Say
is
the
it?
question again?
A 0 wavelength photon is high or low energy? Infinitely high energy, right? Infinitely high energy. 0 wavelength is infinite frequency. If the wavelength is 0, the frequency is infinite because it has to multiply to the constant of the speed of light. So anyway, this is actually high energy. It's just another little thing that gets you. Anyway, now of course the upper limit will be infinity, which is a infinitely long wavelength. By the way, the reason I'm mentioning that, you see how I have an absolute value? It's like, why did I throw that in there? That's because I'm supposed to be integrating energy, but I'm integrating on wavelength, which is 1 over energy. It messes things up and it produces a minus sign. It's not really supposed to be there. Okay, so this ends up being, and again, as I mentioned to you as well, I know that this looks hideous, but reality is it's a bunch of constants, and the business end of this is really not that bad, and you can plug it into Symbolab. I've noticed that the Wolfram website is not working as well for some weird reason, or I've been having a lot of trouble with it, not telling me what a solution is. Like I plug in this integral, I make all the constants a letter Q or something, just something like that, or sometimes I just forget about it. And Wolfram is just not giving an answer. Let's see, what are we really integrating? We're integrating lambda to the minus 5 over e to the constant over lambda. Right, see that? Now don't write this down. I just want to point out how non-scary this really is. It's all just a bunch of constants. It's a bunch of constants. How about I call them a Q? And I've got lambda to the minus 5 over e to some, let's call them a over lambda. Looks like that. Q times lambda to the minus 5 divided by e to the a over lambda. That's what this really looks like. Well, I have to admit, that actually kind of looks scary too, to be blunt. But it's also not like mind-blowing either. I know that I can plug that into Symbol Lab or maybe Wolfram if it's being cooperative. And there you go. So again, you have a bunch of constants, but it's really not too bad. And you end up with 8 pi to the 5th kb t to the 4th over 15. Again, this is all from, I don't know how to solve that on pen and paper. I use a website to solve it for me. That's some other software. And so this is the answer. Okay, and what is this? Oh, notice by the way the L's to the 3 cancels here. Anyway, it's one reason you do that. So, what is that?
Energy density?
Energy density of a? No.
Like
a lot of photons out of what? Of a light bulb, right. This is the energy coming out of a light bulb. What's the biggest light bulb you've ever seen? The sun, right. Now why am I saying so we're done? This was awfully hard, right, wasn't it? Let me wrap up some details with this thing and then tell you some other little interesting factoids about where we got the energy of a photon, and that will lead us into stuff about quantum mechanics. So the Planck distribution, by the way, and you know, I haven't mentioned this before. I didn't mention the name because I don't worry too much about what things are called. Okay, so this is the Planck distribution. Notice that I've put the lambdas together. I didn't up there because I wanted you to see that one lambda to the 4th came from the degeneracy factor, that there's 211, 121, 112, and that other lambda comes from the average energy of a photon. Now I'm putting them together just for convenience sake. And notice all the n's for the number of photons disappeared. Those got summed out. Really not any different than being integrated out. We just didn't need to do an integral. Okay, so this is the Planck distribution, and I'm making a graph. That's the y-axis. Here is the x-axis. And what you get is a 1 over lambda to the, anyway. So it's inversely proportional to wavelength, so it rises kind of sharply, but this guy ends up coming from the Boltzmann factor and ends up pushing it back down. And I have a weird inflection that bothers me. There we go. Okay. There you go. Now, and the inside, by the way, the area of course is HC, is what I just wrote. It's the total. And I'll just write it down again. It seemed very repetitive today. Lambda kBt. Now, let's see what I wanted to tell you about this. Okay. Here's a neat thing. How would you design, here's what we can kind of get out of this. How would you design a better light bulb? You'd want light bulb to produce lots of power. According to this equation, this is the output. Here, it's the same here. This is the output. Now wait a minute. What have I done? No, okay, shoot myself. You know Fridays are bad, right? Here's the integral, it's right here. Sorry, my head just wants to fall off. This is the integral right here, right? Because I just do the area under the curve. Anyway, so now if you look at this, if this is based on how we build light bulbs, which we haven't really figured out anything particularly spectacularly different in a long time, what can you change a light bulb to make it more powerful? What design principle do you see in here that tells you how to engineer a light bulb to make it more? Just get it hotter. Right, so you may be thinking about, oh, what can I learn about light? You know, it's kind of the useful thing about this stuff is you learn how things work. You make light bulbs to produce power, to produce light, energy. This tells you how much light energy is coming out, so it also would tell you how to manipulate it to get more. The answer is, unfortunately, this actually kind of sucks. It just says you can only get it hotter. And that's literally it. And so that's kind of dissatisfying. It doesn't tell you, oh, you need to make it out of molybdenum. Forget tungsten, use molybdenum. No, that's not in here. Unless molybdenum gets hotter. Okay, now that's useful. Okay, so maybe it does tell you some stuff. But it has to all come down to temperature. Okay, here's another thing. LEDs. LEDs, how do they tell you what it looks like? Well, now that we have LED light bulbs. Whenever I buy, because I had to replace all the light bulbs in my condo with LEDs. You know, it's illegal. Yeah, you can't buy incandescent light bulbs anymore. When I buy an LED, there's a number on it that tells me what kind of color it is. What number is that?
Is it a wavelength?
The wavelength is, I mean, that's too obvious, and it doesn't. What is it?
Is it called the number?
Yes, the temperature. Yes, they have a temperature associated with them. It tells you whether it's hot or cold. Right? So anyway, that's why. It tells you the spectrum. Okay, last factoid. The surface of the sun is 5,800 degrees K. How do I know that? Right, because of this equation. Actually, what you can do, if you look at the solar spectrum, you can get a perfect fit to this equation, but you have to make T 5,800 K. And it's a perfect fit. Actually, if you Google this stuff, you'll see some dips, especially around 3,000 and 2,000 wave numbers. Any ideas why? So 3,000, 2,000 wave numbers, you'll see little dips in the solar. I have a spectrometer and I aim it at the sun, and I get this, except I have some weird dips around 3,000, around 2,000 wave numbers. Any idea?
Interferes with the atmosphere?
Yes, specifically what? Absorption. Well, it'd be absorption. Oxygen doesn't absorb light, so it would be carbon. Okay. Water stretches and CO2. Right, CO2 is a very strong absorber. Heard of that before?
Yeah.
It has characteristic bands around 2,000, and then there's water absorbed, OH stretches. Okay, one of you mentioned ozone. What did I draw here? Right, ozone. Ozone prevents, this is the UV region. Ozone causes this to jump down because ozone absorbs a lot of the UV light. So the solar spectrum produces enough UV light to basically kill us all, but the ozone layer absorbs it before it reaches the planet. And that's the only reason that we all don't have skin cancer. It's only because of that. So again, you can fit the solar spectrum perfectly with 5,800 degrees K. I was just pointing out some of the weirdnesses due to CO2, largely due to CO2, because CO2 is incredibly absorptive. That's a vibrational absorption. Ozone, that's an electronic absorption, but there's a lot of ozone, and that keeps the UV light from coming in and killing us all. When the ozone layer, which is coming, there's a hole in the ozone layer, it actually stretched over, now I'm guessing you folks know where Patagonia is? Know where that is? Oh, but what? You don't know? Who's heard of geography? Anyway. Okay, the south of South America is Patagonia. And the ozone layer briefly stretched, the hole in the ozone layer briefly stretched into Patagonia. All the people started getting skin cancer right and left. It was hideous. There's almost no one that lives there, but the people that do, they all started getting skin cancer immediately. And so they're all wearing hats all the time now. So anyway, that's why that matters. Okay, so I'm going to stop there.